So in this video, we want to look at actually constructing a 1 minus alpha times 100% confidence interval for the population mean, mu. So, provided 1. Sample data come from a simple random sample or randomized experiment. 2. Sample size is small relative to the population size, meaning the sample size has to be less than 0.05 times the population size. So the sample has to be less than 5% of the population. And the reason for that is we need independence. So we want the individuals in our sample to be independent. And so we verify that by making sure that the sample size is not too big relative to the size of the population. 3, the data come from a population that's normally distributed, or the sample size is large. Now that is really a big deal. In order to be able to use the t-distribution, we have to have an underlying assumption of normality. The population either needs to be normal, or we have to have a large enough sample size for the central limit theorem to apply. So either we have to know the population's normal, or we have to have a sample size of 30 or more. The reason for that is the student's t-distribution is what is called a parametric distribution. And a parametric distribution means that there is an underlying assumption of normality. And so a lot of statistical work depends on there being an underlying assumption of normality. And anytime that is the case, then we're dealing with parametric statistics. If we do not have that normal assumption, then we have to use other techniques that do not rely on the normal distribution, and those are called non-parametric measures. And so we're not going to really do much with non-parametric measures in this course. We're going to always have this underlying assumption of normality, but if we don't have either a population that's normal, and if we don't have a large enough sample size, meaning 30 or more, then we can't use these techniques. The student's t-distribution is dependent upon data coming from a normal distribution. And so if the underlying population's not normal, or if the sample size isn't large enough, then we can't use the t-distribution because it's a parametric distribution. This is a big deal. Anyway, as long as these three conditions are met, a 1 minus alpha times 100% confidence interval for mu is given by our lower bound for our confidence interval will be our point estimate, x bar, minus t sub alpha over 2 times s over the square root of n, that's our margin of error. And our upper bound will be our point estimate, x bar, plus t sub alpha over 2 times s over the square root of n. Again, that's our margin of error. So x bar minus the error, x bar plus the error, where t sub alpha over 2 is the critical value with n minus 1 degrees of freedom. This confidence interval is often referred to as a t-interval. So we're finding this confidence interval using the t-distribution for a population mean, and so often that's referred to as a t-interval. Now just to formalize what we've said previously, the margin of error for constructing a 1 minus alpha times 100% confidence interval for a population mean is given by E equals t sub alpha over 2 times s over the square root of n. That's what we saw on the previous sheet. And so again, if we take x bar minus E and if we take x bar plus E, this will give us our confidence interval for mu. The procedure used to construct a confidence interval about the mean is robust, and that means the confidence interval will be accurate even when there are minor departures from normality. Remember, a normal population is required by the t-distribution. However, the confidence interval will not be accurate if the data contains outliers, because both the sample mean and the sample standard deviation will be skewed by outliers. So if we have outliers, that's a problem. We can vary a little bit from normal, especially if we have a large sample size, but we cannot have outliers. As a general rule, if the sample size is large, which means n is greater than or equal to 30, we will compute the confidence interval. When the sample size is small, in other words, n is less than 30, we're going to use a normal probability plot, or really we'll use a QQ plot in StatCrunch, and a box plot to verify normality and to check for outliers. So we're going to use a QQ plot as a way to verify that we have a normal distribution when we have small samples. If we have large samples, we're not going to generally worry about it. So if our sample size is 30 or bigger, we're going to generally say we're good to go. If we have a sample that is smaller than 30, then we're going to verify normality by doing a QQ plot. We're going to verify that we don't have any outliers by creating a box plot. So we are ready to look at an example. A December 2019 Gallup poll asked 1,025 adult Americans, which means 18 or older, quote, about how many times in the past year, if any, did you go to a library, end quote. Results of the survey indicated that X bar equaled 10.5 visits. Assuming S equals 15.2 visits, construct a 95% confidence interval for the mean number of visits to the library by adult Americans. Interpret this interval. So we're wanting to construct a 95% confidence interval. So our level of confidence is going to be 95%. And so our sample size is 1,025, which means the degrees of freedom will be 1,024, 1,025 minus 1. We know that X bar is equal to 10.5 visits and that S equals 15.2 visits. And so from this, we need to construct our confidence interval. So we know X bar is 10.5. We just need to find the margin of error. So we need to calculate E. So remember our formula is E equals our critical value, T sub alpha over 2, times S over the square root of N. So we need to figure out what our critical value is. So again, we have this T distribution, and this T distribution is going to have 1,024 degrees of freedom. So we know we're doing a 95% confidence interval, so this area here in the middle is going to be 0.95, which means the area in the two tails total makes up the other 0.05, and half of that's in each tail, and half of 0.05 is 0.025, so the area in each tail is 0.025. So we need to figure out what these critical values are, and so we're going to be able to use those in our formula. So again, how can we go about finding those critical values? Well, we can use our calculator. We can use the T calculator in StatCrunch, or we can use the T distribution table that is provided in the appendix. I'm going to use the T distribution table that's provided in the appendix. So I'm pulling in our table, and we're going to be using the 0.025 column because the area in the right tail is 0.025. And we have 1,024 degrees of freedom. So I'm going to go down this column until I get to 1,024 degrees of freedom. But that's actually an issue for us because this table doesn't have a row for 1,024 degrees of freedom. And this is going to potentially be a problem. Notice the accuracy of our table. The table goes up through 40 degrees of freedom, but then after we get to 40 degrees of freedom, then it jumps by tens. It goes 50, 60, 70, 80, 90, 100 degrees of freedom, and then it jumps to 1,000 degrees of freedom, and then it shows us the normal distribution, the standard normal distribution. So when we get out of our range of specific degrees of freedom, we're going to use whatever's closest. So we have 1,024 degrees of freedom, so the closest thing that I have to that is 1,000 degrees of freedom. So again, using the 0.025 column, that critical value is going to be about 1.962. Now, by the way, the reason why the table doesn't put more of these values in is notice that they get to be really, really close together. So like, take a look at this. With 36 degrees of freedom, it's 2.028. 37, 2.026, not much difference. 38, 2.024, 39, 2.023, 2.021. Even going from 40 to 50, the difference is 2.021 to 2.009 to 60s, 2.000, and so on. There's not a lot of difference in there. So it's only different out in like the thousandths place, and even that's not a whole lot. So it's not a super big deal. Anyway, getting back to the point, we're going to be using 1.962 for our degrees of freedom here in this calculation. So this is going to be 1.962, which means this is negative 1.962. So we're going to use 1.962 for our calculation right here. And incidentally, before I go through with the calculation, I could have also have found this using, say, the calculator or StatCrunch. So if I use the calculator, my command would be inverse t, and let's say I'm going to find the negative side here. So my area in the left tail would be 0.025, and I have 1,024 degrees of freedom. So if I bring in my calculator, and if I go to the inverse t distribution, 0.025 is the area in the left tail, and if I have 1,024 degrees of freedom, so I get negative 1.962 if I round to 3 places, which is actually what we got here, and that means this would be positive 1.962. So again, even if I use the 1,000 degrees of freedom instead of the 1,024 degrees of freedom, it doesn't cause a big problem. To 3 places, they're the same. So anyway, my critical value is 1.962, so I'm going to multiply that by S, which is 15.2, divided by the square root of the sample size, and the sample size is 1,025. So if I bring my calculator back in, 1.962 times 15.2 divided by the square root of 1,025, that is 0.9315. So we have a margin of error of 0.9315. So my confidence interval is going to be my point estimate, x bar. So that's going to be 10.5 minus 0.9315 to my point estimate 10.5 plus 0.9315. So bring my calculator back in. 10.5 minus 0.9315, that is 9.5685. And 10.5 plus 0.9315, that is 11.4315. So 9.5685 to 11.4315 would be my 95% confidence interval. And typically, since our statistics here are only given to 1 decimal point, it doesn't really make sense to carry our confidence interval out to 4 decimal points. So typically, if these are rounded to 1 place, the most we will go in our confidence interval would be like 2 places. So probably it would be better if I round this and say 9.57 to 11.43. That would be our confidence interval. Now we also want to interpret this interval. So our confidence interval is 9.57 to 11.43. So interpretation. Now we did a 95% confidence interval. So our interpretation, we are 95% confident that the true mean, meaning the population mean, number of visits to the library is between 9.57 and 11.43. In other words, we're 95% confident that on average an adult American visited the library somewhere between 9.57 and 11.43 times. That's what we're saying here. Now again, with 95% confidence, what that really means again is that our statistical methods will give us a confidence interval 95% of the time that actually contains the true mean. So again, we're 95% confident that the true mean number of visits is between 9.57 visits and 11.43 visits. In the next video, we're going to revisit this problem, and I'm going to show you how to directly find a confidence interval using technology. So we'll show you both on the TI-84 calculator and StatCrunch how to go about constructing this confidence interval.